And you can wrap it, and you can put it in your pocket.
I see, okay.
The next speaker is Charles from the University of Chicago. The topic of his talk is analytic robust confidence intervals possible.
Thank you, Christoph, and I would like to thank the organizers for the kind invitation. It's great to be back here another year. Today I'm going to talk about robust confidence interval, and this is a joint work with my wonderful collaborator Yuetian Luo, who is currently a data science postdoc at UChicago. He has been doing amazing work in the past 2 years with both me and Rina, and I don't think the project could be finished without his huge contribution. He is currently in the job market. So I'm going to start the talk from this very simple example that you get to observe IID data from normal theta 1, and the problem is to construct confidence interval for the parameter theta. The problem has a standard solution that is given by this one, interval centering at the maximum likelihood estimator. Radius of the interval is given by 1/√10. And from stat 101, we know that this interval not only has the desired coverage, but actually among all intervals having the coverage property, this one is the shortest. So in today's talk, what we are going to do is to extend the classical result to the modern setting where the data may have outliers or contamination. In particular, I'm going to consider the problem in the setting of Huber's contamination model. So instead of assuming IID data from the correct model, we assume data is generated from this mixture distribution, also involves a contamination distribution Q. So you can think of the setting where there is an epsilon fraction of the data that can be arbitrarily generated from some distribution. I want to emphasize that in Huber's setting, the contamination distribution Q does not have any assumption. It can literally be any distribution. So the outliers can take any arbitrary numbers. Okay? I'm going to call epsilon by the contamination proportion. This is a very important parameter. And still, I'm going to ask the question, how do you construct confidence interval for the location parameter theta in such a setting that involves outliers? So let's start with a brief review of what we know about optimal estimation. I think this is already very well known to this audience, that the sample median is a rate optimal estimator for theta. The error rate is given by 1/√10 plus epsilon. You need to have this additional additive factor epsilon besides the parametric rate of 1/√10 because of the contamination effect. In fact, 1/√10 plus epsilon is the minimax rate of the problem. So that means the sample median is a rate optimal estimator. Okay? Now, if you want a confidence interval, one thing you can do is to rewrite this high probability error bound into this form. Then this gives you obviously an interval that centers at the sample median. The radius is given by 1/√10 plus epsilon. And obviously this construction is a valid construction because it still satisfies the coverage property. The two probability events are the same. And moreover, this interval is also rate optimal because the length of the confidence interval cannot be shorter than a high probability error bound, right? So what's wrong with this interval? Well, the problem is if you want to use the formula, when you write it down, you need to know the value of the contamination proportion epsilon, right? Of course, in practice, this number is usually unknown. And what's even worse is I previously said that the contamination, because the contamination distribution Q has no assumption, the contamination proportion parameter is actually a non-identifiable parameter. So if you simply try to estimate epsilon and plug in, this will never work. But nonetheless, we are still going to ask the question, is it possible to construct confidence interval for theta, even if the contamination proportion epsilon is unknown? Well, let's first lay down the mathematical formulation of the problem. What we need is a confidence interval, which is a random interval, which is a set function of x1 through xn. We can write down two requirements. The first one is coverage, that requires the interval that covers the truth with probably, say, 95%. And then we also have the length requirement that the length of the interval is bounded by some function. Here, the function is a function of both the sample size n and also the contamination proportion epsilon, okay? And since I want to deal with the situation that epsilon is unknown, so we also put infeynman over epsilon over the entire interval from 0 to 1/2. That makes sure that the two properties hold uniformly over all epsilon. Then whichever C hat that satisfies these two properties simultaneously is going to be called an adaptive and robust confidence interval, okay? And the question I'm going to address is, among all adaptive and robust confidence interval, which one has the shortest length? In other words, what is the smallest R that I can put here? Yes, Elias.
So I said this before, but I want to ask something crazy. So if you take this infimum between 0 and 0.49, does the problem become easier?
Actually, it should be 2.49. 1/2 does not work, just to simplify my presentation.
Okay, so the 1/2 there is not important.
The 1/2 should be 0.49. But you can further ask, what if it's not 0.49, it's 1/3, then there's no difference. As long as there's a constant strictly below 1/2. Okay, thanks for the question. All right, so if the formulation is clear, then we are ready to see the first result, that we show that, at least for the Gaussian distribution, any adaptive confidence interval that satisfies the coverage property, its length must be lower bounded by this rate that consists of two terms, 1/√log n plus 1/√log 1/epsilon, okay? I want you to compare this lower bound rate to the previous non-adaptive rate, 1/√10 plus epsilon, which can simply be achieved by the medians that centers at the interval that centers in the median, okay? So this comparison shows you that if you do not know the value of epsilon, there is a huge adaptation cost that you have to pay, okay? Even in a situation where epsilon is 0, that means the data is clean. You have 100% clean data, right? As a consequence, the second term simply disappears, but you still have the presence of the first term, which is of order 1/log n. Okay? Then compare with the parametric rate 1/10, you still have to collect exponentially more samples in order to achieve the same accuracy of incident quantification. This is because, yes, you may have 100% clean data, but just because you do not know whether your data is clean or not, then you still have to pay this price. Okay? So in addition to this lower bound, we have an explicit construction of the upper bound that achieves the optimal length. The upper bound construction is based on empirical CDF. The inverse of the CDF is called the quantile function, which is basically just the order statistic. So this particular formula, based on order statistic, does not depend on epsilon, and it can also be computed in approximate linear time because of order statistics. And we show that it satisfies coverage and its length matches the previous lower bound. Okay? Well, so the question you may be wondering is, how can we actually derive this formula? Is it from some random inspiration, or there is actually some general principle that we can apply? And the second question we want to address is, why do we have to pay such a huge cost for adaptation? So in order to answer both questions, yes.
I'm a little confused.
Okay.
Let's say if I know my epsilon is very small, it's less than n to the power minus 5.
Then, okay,
Then
so.
you get something like log n here, right?
Yeah, so if you know, let's say epsilon is small.
Just give me a range, less
Yeah.
than n to the power minus 5.
So here the result says, the result applies to the setting where you only know the epsilon is smaller than a constant.
Sure.
But if you know the epsilon is actually smaller than something that goes to 0, then you can do better. There is a more general result to cover that case. Okay. Thanks for the question. All right, so yes?
You have the same result if epsilon can take only two values, like 0 and 1/3?
Exactly, it's the same. So if epsilon takes two values, you will actually see this result later. Yeah. Yes.
You also said before that even if epsilon is equal to 0, it so happens that epsilon is equal to 0, you still have to pay this quality again. It's because there's no way to test if epsilon is 0, right? It might be 0 or a third. Information theoretically, these are
Yes. Yes. Any other question? Okay, so as Ilya suggested, I'm going to tell you a related hypothesis testing question, which I think is the mathematical essence of this problem. So this particular testing question that we are going to look at is this one. The null hypothesis says that the data is from normal theta 1. Alternative says that, okay, data is actually have a location shift. The location parameter is theta plus r, but you also have 50% contamination, okay? So not only are you trying to distinguish between theta versus theta plus 1, you are also trying to tell difference whether the data is clean or the data has 50% contamination. I want to emphasize here that both number, theta and r, they are fixed parameters. That means the null hypothesis is simple. It only contains a single distribution. Alternative, on the other hand, is composite because Q is allowed to vary. So to be more precise, alternative hypothesis contains all distributions that can be written in terms of this mixture for some Q. Okay? Then the question we are going to address is, what's the smallest separation R so that we can distinguish the two hypotheses? Well, the reason this hypothesis testing problem is important is solving that implies the solution for this construction of the robust confidence interval, which gives you adaptation over 2 points, either epsilon being 0 or epsilon being 1/2, which exactly address Pierre's question. Of course, this is just a subproblem. Epsilon is not over the entire interval, but let's start with the solution of this one and then see if we can extend to the full generality. Okay? So to be more precise, suppose you have a solution for the construction of confidence interval, you can actually construct a testing procedure by rejecting the null hypothesis whenever the alternative parameter theta plus r is covered by the interval. Then as long as alpha and beta are small, you can also prove small type 1, type 2 error for the corresponding hypothesis testing procedure. The reverse direction is also true. Suppose you have a testing procedure, you can actually invert it into a confidence interval that collects all theta plus r such that the corresponding alternative is accepted, okay? So having understood the equivalence between the two problems, let's try to focus on solving the testing problem. Here, for simplicity, I'm going to take theta equals 0 because this is a location model. You can just translate your parameter to get a general solution. Okay, so let's start with the upper bound. How do you solve a hypothesis testing problem? Well, it's a standard procedure. You try to write down some testing statistic and to show the statistic is small and the null and large and the alternative. Then you can just reject the null whenever the observation is large. The statistics that we are going to look at is the indicator function, which captures the information at the tail. So let's try to understand the magnitude of the indicator under both null and alternative. The expectation under the null is just a standard Gaussian tail. If you want to characterize the expectation under the alternative, because you do not have any assumption on the second component of the mixture, the only thing that you can say is the magnitude is lower bounded by the contribution from the first component, which is 1/2, again, times the Gaussian tail, but this time you have a location shift R, okay? Of course, what you need is the lower bound under the alternative is much larger than the expectation under the null, right? So as long as this inequality is satisfied, then you have separation at least in the population level. Of course, the actual statistic is the empirical version of the indicator, right? You need to use the empirical average of the indicator function. So what you also need is the concentration between the empirical indicator and the population version. We know that the empirical average of indicator is just the empirical average of Bernoulli random variables. Empirical average of Bernoulli random variables concentrates around the Bernoulli mean if and only if the Bernoulli mean is at least of order 1/n. Okay, so this is another requirement you can write down. Actually, the first requirement tells you that you can choose t to be of order root log n. Once you plug the choice of the t into the second inequality, then you can show as long as r is greater than 1 over root log n, then you can separate two hypotheses. Okay? This is how you can solve the upper bound. Now let's try to get the lower bound. We want to find a threshold such that whenever r is smaller than the threshold, you can no longer distinguish the two hypotheses. So the idea is to construct a Q such that the null looks almost the same as the alternative. Okay, how do you construct such a Q? Well, you can first try to find a Q such that the null and the alternative, they are exactly the same. Okay, so this gives you an equation that normal 0, 1 equals 1 over 2 times normal R1 plus 1 over 2 times Q. And then you get the solution. But pay attention here, I put a question mark. Okay, so this solution is actually not a valid probability density function because a valid probability density function needs to be positive and it also has to have integral 1. Okay, so this formula, of course, it has integral 1, but you can show for no matter what r you choose, you can always find an x such that this function is actually negative. So it can never be a valid construction of probability. There is a simple fix though. You can apply this truncation. So the idea is we are only going to use the formula on the bounded interval from negative t to t. Outside of the interval, I'm going to just set the function value to be 0. And then after normalization, that's a valid construction of probability distribution. Okay? And the requirement is the function now needs to be positive on the bounded interval, which is equivalent to, again, the comparison between the two Gaussian tail. Okay? And of course, because of the truncation, now you don't have exact match between the null and the alternative. It's actually approximate match. So the requirement is the parameter t should satisfy that the chi-square between the corresponding null and the alternative needs to be bounded by 1 over n because this is a sufficient condition so that you cannot distinguish the two hypotheses with NID samples. Okay? Now, if you can compute this chi-square divergence, because the error is basically coming from truncating out the Gaussian tail, so the chi-square is basically determined by the Gaussian tail. Right? So you need Gaussian tails more than 1 over n. Again, this corresponds to the choice of t to be of order root log n. And if you plug the choice of t into the second requirement, then you can show if r is smaller than 1 over root log n, then you can no longer separate two hypotheses. So basically, the upper and the lower bound derivation, they are exactly the same. Okay? Well, let's try to summarize. What we have is the solution of this hypothesis testing problem. The optimal testing procedure is this testing function. You reject the null hypothesis whenever the empirical average of the indicator is greater than 2 times the expectation into the null. Okay? And now let's try to invert this testing procedure into a confidence interval. So this is how you can do the inversion. You collect all theta plus r such that the corresponding null is accepted. So by the definition of CDF and the quantile function, so it is all theta plus r such that theta is bounded by this quantile minus t. After a variable change, it's all theta that is smaller than this quantile level minus t plus r. Okay? So you may be wondering, so here this is not an interval, right? It's just the half of the interval. Where is the other half? The reason that we don't have the other half is because here the alternative hypothesis is just a plus r. If you want the other half, you need to also consider minus r. But then the derivation of the other half is exactly the same, following the same mathematical derivation. So I'm going to ignore that. Okay? All right, so for this formula, remember that previously we choose t to be of order root log n and r to be of order 1 over root log n. So the relationship between t and r is 1 over t. Okay, so at this point, if you look at the formula, it only depends on t, so it's pretty clean. So previously I said if you can solve this particular hypothesis testing problem, then you will be able to obtain a robust and adaptive confidence interval that is adaptive over 2 levels of contamination, epsilon either being 0 or epsilon being 1 over 2. Okay? If you want an interval to be adaptive over all levels of epsilon, you should actually solve this more general hypothesis testing problem where the null hypothesis now have contamination level at epsilon. However, actually the solution for this more general hypothesis testing problem follows exact formula. The only difference is now the choice of t should vary if you change the value of epsilon, okay? So in the end, if you want your procedure to be adaptive over all epsilon, one trick you can do is to have the intersection of the interval over all t, okay? And this is how you can arrive at this formula that is adaptive over the entire range. Any question at this point? Okay, so at this point, we've been focused on the Gaussian model, and for those of you who are familiar with Gaussian, that you may already have the intuition that the 1/root log n rate is precisely coming from the Gaussian tail, right? So one natural question is, what happened to other distributions? What if the distribution does not have a Gaussian tail? Let's take a look at an example. So let's say we have a Huber contamination version of Laplace model. Let me remind you that the Laplace location model has an exponential tail compared with the Gaussian tail in the Gaussian model. Then we can ask the same question, okay? So for the Laplace mean, how do you construct a robust confidence interval, okay? So previously for the Gaussian, the optimal interval length is 1/root n. Anyone want to guess the rate for the Laplace case? Harry.
1/n to power something?
In a-
I mean, let me, oh no. Should be wider, right?
Yeah.
Much wider.
Yeah. So the intuition is correct because the tail is now heavier, so the problem is harder. You should get something even slower than 1/root log n, okay? So that's the correct intuition. And in fact, it's much worse than that. We show that for Laplace distribution, you cannot do better than constant rate. Okay, so that means you may have an endless supply of clean data. N equals infinity, epsilon is 0. But just because you do not know whether your epsilon is 0 or 1/3, for example, it's impossible to get a shrinking confidence interval no matter how large the sample size is. Okay? So why do we have such a difference between Laplace and the Gaussian? Well, let's try to take a look at the corresponding testing problem again. For the Laplace version of the testing problem, you can actually find a Q that exact match the null and alternative without doing any truncation, okay? And you can do so even if R is of constant order. In fact, as long as R is smaller than log 2, then this particular construction is a valid density function because it stays positive for all x. The reason it stays positive for all x is just because of the property of the Laplace tail. For Gaussian, you don't have this property, you have to do truncation, okay? So you cannot tell the difference between the following two situations. The first situation is data are all from Laplace with mean 0. The second situation is data is actually coming from Laplace with mean R, but also with 50% contamination. Because I do not tell you the contamination level, you do not know whether the mean is 0 or R. That explains why you cannot do better than constant, okay? So in fact, we also take a look at some other distributions. So here are some examples that we list distribution from heavy tail to light tail. T distribution has a polynomial tail. Here, the generalized Gaussian, it contains Laplace, includes Laplace and Gaussian as special cases for different values of beta. And these two examples, modifier and Bates, they are distributions with boundary support. Modifier, it's exponentially smooth at the boundary. The Bates distribution is defined as the convolution of independent uniform random variables. For example, k equals 1, that's uniform. K equals 2, that's like a triangle-shaped density. Now, if you want to estimate the corresponding location parameter, they are all the same, right? The sample median achieves the 1/root n plus epsilon, and for each of the distribution, you can prove a matching lower bound. And if you want to construct confidence interval, let's say you know the value of epsilon, then it's also the same because you can just use the median confidence interval. However, if you do not know the value of epsilon, then they are all different. It's actually case by case. And the optimal length of median is summarized in the last column for t-distribution. Because it's heavy tail, you cannot do better than constant. Generalized Gaussian has this logarithmic rate. If you pay attention to this exponent, the exponent is on the numerator. It's the positive part of beta minus 1, right? So that means this rate goes to 0 if and only if beta is greater than 1. So that means the Laplace distributions is actually the boundary between what is known as the shrinking confidence interval versus non-shrinking ones. So a robust confidence interval can shrink as the sample size goes to infinity if and only if the tail is lighter than Laplace, okay? And for modifier, you get an even faster logarithmic rate, but for Bates, since there are more information at the boundary, you can even get a polynomial rate, okay? Any questions? Yes? So k equals 2 for this one, it's still this formula. But this one, it's different. I think for this one, the rate will change to, inside the square root will be n log n, right? Because for k equals 1, it's uniform. For uniform, you don't have 1 over log n, you have 1 over n. So k equals 1, k equals 2, they are special.
So the confidence interval length formula will still be same?
Sorry?
For the confidence interval length?
Yes, yes, yes. That's exactly correct. So actually, the uniform distribution is probably the only case that you don't have an adaptation cost. Please.
If you take the Uber distribution, which is Gaussian at 0 and Laplace infinity.
Sorry, could you say it again?
Uber's the worst case distribution for Uber's so Gaussian at 0 and Laplace at infinity.
Oh, and then it'll be constant. It's really the tail that matters. It'll be precisely behave like Laplace. What happens in the bulk of distribution does not matter. It only depends on tail. Very good question. Yes.
So I suppose you analyzed here some specific cases, but the framework and this reduction to testing is more general. Right?
Yes.
For example, these are all symmetric, right? If I see.
It doesn't matter. Even if you don't work with location model, for general model, the relation is general. Actually, I'm going to, okay, so if there's no other question, I'm going to move on. Okay, please.
The lower bound on the tail, that matters.
The lower bound on the tail is not sufficient. You need both upper and lower bound on the tail. You need to know precisely the tail. Then you can determine the optimal interval length. Okay, so this is the first part of the talk that we have been focused on, at least the location model. Oh, another question?
Yeah, quick question, sorry. So you're taking this epsilon in an interval from 0 to 1/2, right? Have you tried to, instead of taking 1/2, just taking some epsilon max, right? Instead of being like 1/2. But I'm curious, starting which epsilon max you get this behavior for Laplace.
As long as epsilon max is constant, then it's the same result. But a more interesting question is, what will be the dependence on epsilon max? We can also work it out, but it's more complicated. Yeah, it's not hard. All right, so the second part of the talk is going to be move away from the location model. But before doing that, let me actually discuss one extra point. This is the point of unknown scale, that the variance is unknown. The reason I want to discuss this point is every time I give this talk, someone in the audience will ask the question, Chao, what happens if the sigma square is unknown? I'm actually surprised no one asked this until this point. Okay, but now we have seen the question. And it's really a question that, it's also a question that matters in...
Because we are in France.
It's also a question that matters in practice, right? So, okay, that's why no one asked this question. In practice, you never know sigma square. So let's try to see what happens if sigma square is unknown. But the first thing we can do is to write down the setting. So let's first assume sigma square is not necessarily 1, but known, okay? If you knew the value of sigma, then a simple rescaling of the previous construction would work, right? So you can show the scaled version of the count interval still achieve the optimal rate. Okay, so this is easy. Now, if sigma is unknown, what we also know is there exists a robust estimator for sigma. Okay, you can simply take the median absolute deviation multiplied by some constant. That will achieve this optimal rate of estimating sigma, which is of order 1/√10 plus epsilon. Okay. All right. So I want you to compare these two rates. Right. So it turns out the estimation error of sigma is much faster than the optimal interval length of location. So you may expect that a plugging procedure would work. Right? This is exactly what I told my collaborator Beitian. I said, you should go back and just to prove it. The next day, he came to me, he said, Chao, it doesn't work. Then I was like, what do you mean by it doesn't work? Let me say it again, right? So the intuition is the estimation error is polynomial, but the optimal interval length is just logarithmic. So if you plug in the error, the actual error is negligible, right? So if you still couldn't prove it, why don't you try sample splitting? Then he said, I've already tried, it doesn't work. Okay, so now at this point, we start to take the problem more seriously, and then he was right, because I couldn't prove it either. And actually, it doesn't work. Not only the plugging procedure does not work, nothing works, okay? So the subtlety of unknown sigma can be summarized in this table. So what we care about is this entry, right? So if you do not know epsilon, and on top of that, you do not know sigma, then you can only achieve a constant rate. It's very much like the Laplace case. Then the sample size does not matter anymore. Okay? And I want you to compare the first column with the second, right? So the first column says if you knew the value of epsilon, then knowing sigma or not does not matter. But if you do not know the value of epsilon, then unknown sigma will give you additional adaptation cost. Okay? So in practice, this means that if you do not know sigma, then almost you can do nothing.
Sure.
Yes.
Slightly related question. So your results are very pessimistic at many points, and this is because your Q is whatever.
Exactly.
Yeah. So I mean, what about considering, say, some classes of Q?
Yeah.
Parametric or non-parametric, and so if you have this additional.
Great. Next year I will give that talk. Of course, that's the next step.
But his Q is already pretty nice, right? It's just compare difference of the algorithm.
Yeah, what you mean by very nice? I assume you mean it's smooth, right? But
yeah,
there may be some additional structure.
Very simple structure. That's what I mean.
Yeah. Okay. There are some reasonable assumptions on Q that you can actually avoid this specific assumption. Yeah. Okay. But that's another topic. All right. So how many minutes do I still have? Oh, great. Okay, I still have time for part two. So part two is let's try to discuss something that is not location model and then see what can be different. So I'm going to start with discrete data, and in particular, start with the simplest setting, that is the Bernoulli model, okay? Because this is even simpler than Gaussian. Now I claim you can actually solve this problem by just staring at it, because this is so simple, right? First to realize the worst case contamination Q must have the same support as Bernoulli, right? Because if for some reason Q generates a 2, then of course you know it's outlier, you just throw it away, of course, okay? So without generality, you can assume that Q is Bernoulli. Then, Bernoulli is actually linear in terms of parameter. In particular, you have this relation. So if you happens to have data that contains approximately 50% 0, 50% 1, then really you cannot tell whether it's actually from Bernoulli half or maybe it's actually from Bernoulli 0. You just happen to have 50% contamination, okay? So that means if you do not know the contamination proportion, you cannot do better than constant incident quantification. So that's for Bernoulli, the message is it's impossible, the problem is solved. Okay, so let's try to look at a more complicated example, which is more interesting, binomial. The reason this may be non-trivial is because for m gets large, binomial looks more like a Gaussian because central limit theorem, right? So we know for Gaussian you can do something non-trivial. So maybe for this case, you can also do something non-trivial. And this is precisely the correct intuition. And that's the result that we get for binomial distribution. We show that the optimal length of the confidence interval, if you do not know epsilon, has this formula. It contains the summation of two terms. The first term is precisely the Gaussian rate. You just have this additional 1√m as a scaling factor because of the standard deviation coming from the parameter m. And you still have the second term. Okay, so a special case is if m is constant, then because of the second term, the entire rate will be constant, which covers the Bernoulli as a special case. So this formula sort of nicely interpolates between Gaussian and Bernoulli. Okay? Of course, I can tell you about how to construct this confidence interval, which is itself very interesting, but I decided to skip that. In fact, the reason I want to, I talk about this binomial example is to prepare for the next example. I think this is the most interesting example.
So can I ask a question about the previous one, about the binomial? I'm surprised that there is no dependence on like m times p or something. Because like for p, that is product.
That's a great question. So here, if you want to track dependence on p, it will be square root p times 1 minus p.
Okay, so
but I just assume p is constant.
This is close to Gaussian, not close to Poisson.
It also covers the special case of Poisson if you take p equals, yes, yeah, yeah, just for simplicity of presentation. All right, and you may ask the question again. In this case, then it will be the same answer.
I guess the interesting part over here is 1 over n, right? That's mainly the interesting part.
The interesting part is actually to prepare for this example. Oh. Okay. So in this example, what we are looking at is an Erdős-Rényi model, but an Erdős-Rényi model with contamination. And then how do you still construct confidence interval for the parameter, okay? Now, in a network setting, there are two ways that you can model contamination. One way is called edge contamination that says that there is an epsilon fraction of edges that are contaminated. Right? The adjacent matrix Aij take arbitrary value on this contaminated set. But mathematically, that's not interesting because it will be exactly like the previous Bernoulli example. Okay? A more interesting setting in the literature is called node contamination. That says there's an epsilon fraction of nodes that are contaminated. And in terms of adjacent matrix, this is saying that you have an epsilon fraction of rows and the columns such that the connectivity to these nodes are arbitrary. Okay, so here the model says you have a clean subblock, and then in these rows and columns, it's going to be arbitrary. Okay, and then how do you construct confidence interval for the parameter p? I want you to compare with this setting where you only have row contamination, but you do not have column contamination, right? So these two settings are actually very similar. So actually, the second setting, this is exactly equivalent to the binomial Huber contamination model, right? Because if the row is not contaminated, then the sufficient statistic is just summation, which follows exactly the binomial distribution, okay? So the question is, are these two models different or are they the same? Well, if you look at the estimation error in terms of optimal rate, then it's actually the same. Right? So for both cases, it's 1/√10 times 1/√10 plus epsilon. The first rate is not very hard to prove. The second rate is actually, I think it's highly non-trivial. It takes a whole paper by Acharya, Jane, Kamask, Suresh, and John back in 2022 to get this rate. So a very clever idea in this paper. Now, if you care about the optimal adaptive confidence interval lengths, it turns out they're different. Okay. For the binomial model, it's this rate, which is a special case by taking m equals n. However, for Erdős-Rényi model with node contamination, then it's a different rate. It's 1/√10. Okay. Well, if you look at 1/√10, you may think it's not bad, right? But I claim that 1/√10 is the worst rate that you can have in this case, because it's precisely the previous is precisely this estimation rate by taking epsilon to be constant. Okay, so this says even if your epsilon is small, you just pretend it's large, and then you totally give up on the adaptation, pretend it's the worst case situation, right? So that means adaptation is impossible. Okay, so why do we have such a subtle difference between the Huber's model and network model with node contamination? Well, let's take a look again at this corresponding hypothesis testing problem, right? So here you are trying to distinguish between these two hypotheses. The now is Erdős-Rényi model without contamination with mean P. Alternative is parameter Q, but you have 50% contamination. Okay? Then how do I design the contamination pattern? Well, I'm going to choose the contamination pattern in this way. Well, for those of you who are familiar with networks, this is a stochastic block model. Okay? So it turns out we can just take the lower bound for the detection between Erdős-Rényi and stochastic block model. That will give you the 1/√10 error rate. In particular, you can show as long as you have an adaptive confidence interval for robust for Erdős-Rényi model with node contamination, then you can actually turn this confidence interval into a test between Erdős-Rényi model and stochastic block model. Okay, and since Erdős-Rényi model and stochastic model need to be separated by 1/10 in order to be tested, so the confidence interval length cannot be lower than that. Okay, that explains the difference. All right, so that's what we have for the network data. So finally, let me briefly talk about a high-dimensional extension, the multivariate case. So previously, we have been focused on the inference of one-dimensional parameter. What if we have a multivariate parameter? Well, it's the same mathematical formulation, but this time we don't have a confidence interval. Let's say we have a confidence set. And then you can write down the same coverage and the length property. So here the length is actually the radius of the confidence set, right? So now the optimal radius will be a function of the sample size and the dimension P and the contamination proportion epsilon, okay? So the result that we get is that the optimal radius of a confidence set cannot be better than that, and moreover, you can have an algorithm to achieve this lower bound. Okay, I'm actually going to skip the construction of the confidence set. I mean, the main takeaway is here, even though we have a matching upper bound, this particular confidence interval that achieves the optimal radius, but in order to compute that, it's actually not a polynomial time algorithm. So currently, it's still an open problem how to do this multivariate construction of confidence set in polynomial time algorithm, and we are still working on that.
So the difference is to calculate R hat.
Yes.
The difference to calculate the radius.
Yes. So it's basically the computation of this radius that is hard. Okay. Thank you. All right. So this is my last slide. There's nothing on this slide. It's just my comment. My last remark is I think there is a very interesting connection between robust confidence set and this area called list decodable estimation. I think there is a difference between robust estimation and robust confidence interval or robust confidence set. For robust estimation, you cannot really do anything if the contamination proportion epsilon is above 1/2, right? So you have to have less outliers than inliers in order to estimate the parameter. However, for robust confidence interval, confidence set, if you think about it, it's actually possible to do something even if epsilon is greater than 1/2. Right? Let's say you have 90% outliers, you only have 10% clean data. You can still construct a robust confidence set, as long as you don't want you give up the shape constraints such as interval. For example, you relax the constraint to allow the confidence set to be a union of intervals or a union of balls. Then this is possible. Right? This is very much related to the area called list decodable estimation. What list decodable estimation does is precisely in the setting where you have, let's say, 90% outliers. So the list decodable estimation algorithm will output a list of, say, 10 candidates, for example, and the guarantee is that one candidate in the list is prove to be close to the truth, okay? And what you can do in this setting where the majority of the data is outlier is first run a least decodable algorithm, and then you can actually expand each candidate in the list by a Borel interval, and then this is going to be a robust confidence set or confidence interval that covers the true parameter even when the majority of the data is outliers. And moreover, you can show that there's an adaptive property in the sense that if epsilon is actually small, then the unit of Borels will shrink to just one Borel, and the unit of interval will shrink to just one interval in the low-dimensional case. Okay, so this is the last point I want to make, and thank you for attention.